Today we have Pavel Tumarkin from Durham University, and he's going to tell us about non-integer quivers, mutations, and unfoldings. Take it away.
First of all, I would like to thank the organizers of the whole program and of this seminar for the opportunity to be and speak here. I want to talk about mutations of non-integer quivers. I will say in a minute what. Yeah. So this is based on joint work with Anna Felikson and also joint project with Drew Duffield, which is still somehow deep in progress. So I will start with mutations. I want to say who the quivers are. So I take V, the skew-symmetric matrix, with real angles. And to such a matrix, I can associate a quiver Q with usual quiver, which is needs somehow in cluster algebras, but somehow it will have real weights of arrows. And mutation is defined as usual. Rule for mutating skew-symmetrical matrix B from Zelinsky, we just use exactly recall you. So if we have with weights P, Q, and R, and we mutate it in these vertex, then we will get quiver in both directions, E minus R, where R and minus R can be negative. So negative weight means that the negative weight means that the arrow is directed, it has opposite direction. So this is mutation. Now some examples. Where do they come from? So first, and somehow the most interesting for us, are non-crystallographic root system, which I understand in the sense of the order. So which means that we have vectors of equal length, well, normally of length 2, and they satisfy all properties of the root system, except for crystallographic condition of integrality of the Kaplan matrix. So, in particular, finite ones, which are H4. To H4, we associate this quiver, right? And here the weight will be 2 cosine pi over 5. There are 4 vertices, 3 arrows, H3. Probably I've used the notation and write pi over 5 instead of, I will forget about the cosine. Yeah, but the actual weight, the entry in the matrix will be 2 cosine angle, and I2 of m, which is over. These are finite non-crystallographic root systems. And another large class of non-integer quivers, somehow, which can be dealt differently with. These are diagrams of integer skew-symmetrizable rescaling. Okay, so, and I will heavily use this procedure of rescaling, so let me write a definition of it.
Pi over 5 means cosine and pi over m means cosine.
These, well, means exactly the same as these. This is 2. This is pi. This is 5. Well, if they all look the same, well, I'm sorry.
No cosine, just pi over 5.
No, this is 2 cosine of pi over 5. This is the next one. Next one is exactly the same. This is 2 cosine of pi over 5. Yeah, but well, this is a bit longer than this one. I will just shorten the notation in a better way. So this is already bad. So
was
well,
perfectly mistaken.
So here, probably I should apologize because, well, of course, this notation is not compatible with Caxton notation. Compatible with quiver notation, but since they both are not compatible with each other, so okay. So what I wanted to say, I wanted to say what rescaling is. Let me write it here. Rescaling, which was introduced by Nathan Reading. So let us take two skew-symmetrizable matrices. P and B prime are skew-symmetrizable and we say that is a rescaling of P if there exists a diagonal positive matrix S B prime is a conjugation of B using S. So that Ij prime is equal to Ij multiplied by Sj, Sj, and divided by Si. And in this case, I can prove that K of P prime is equal to S inverse K of P. So that the procedure of rescaling commutes with mutation. Which in its turn means that we can consider the skew-symmetrizable diagrams of skew-symmetrizable matrices. No, I have done why. Yeah. Okay, so we have this, yeah, and in particular, if we take D such that BD is skew-symmetric, positive diagonal matrix, which skew-symmetrizes matrix B, then that's right. We can take B prime, which is square root of D inverse times B times square root of D. And it is not a very difficult exercise to see that this is using. These ones also as quivers with. It was about let me show one elementary example. The most elementary example, let me take b to be 0 minus 1 to 0. Whether here is 1, 2, so I take s to be 1 square root of 2. So after that, we get b prime to be 0 minus square root of 2 square root of 2, 0, which somehow corresponds to what we want to see. Yeah, so b, this is root system with angle between the roots 5 or 4, and this also gives root system with angle between roots 5 or 4. But here the lengths were different of the roots. That's all. Now, so what we want to do, yeah, we want somehow to attach some structure. So to these quivers. Something like, well, in integer case, we have x variables, we have y variables, we have polynomials, we have a lot of different structure. Now the question, can we do anything like that here? So what about some variable or something like that? Some observation by Philippe Lampe shows that there's not too much hope for x variables. Yeah. So let me consider the following a bit more general case. So matrix 0 minus p q 0, where p and q are real numbers. Considered the matrices of type 0 minus 1 4 cosine squared pi over m 0. So in some sense, the best possible ones. These correspond to root systems, just I to m, but with again with different sizes of different lengths of vectors, and he considered the corresponding map. So xy goes to 1 plus x to the q. Sorry, 1 to y to the p over x y, and x 1 plus x to the q over y. Yeah. And he showed that there's no periodicity. Something like approximate periodicity. Yeah, so that after n plus 2 steps, your x and y come very close to the initial, but not precisely the same. Which somehow means that, well, you cannot define x variables using usual rules, and if you rescale this, actually rescaling does not preserve somehow the dynamics of x variables, but well, it doesn't become that. And there's a recent paper by John Machajczak and Nick House, where they considered again similar somehow dynamics, and they had the following observation. Then when you start doing somehow iterative mutations, you take the point and you take the orbit. Then there are some ovals, and somehow the whole orbit goes around this oval. Yeah, but this is just experimental data, as I understand.
It's not proved.
Well, yes. So this is an experiment. Yeah. Experimental. There's something behind that, but it's not clear what happens. However, there's a better situation in tropical case for tropical mutation. What I mean by tropical mutation is that you take your matrix 0 minus p, u 0, t1, and t2. The image of the pair t1, t2. So t1, t2 goes to mu of t1, t2. Here, in case of matrix 0 minus 2 cosine pi over m, 2 cosine pi over m. Yeah, there's periodicity. Of this map. Yeah, with period, roughly speaking, m plus 2. Yeah, so in even case, we get just periodicity m plus 2 with after m plus 2 steps. And in odd case, after m plus 2 steps, you need to do additional reflection x goes to 1. Which swaps the variables. Okay, and actually there's somehow a geometric explanation of these. Let me.
Sorry.
Yeah.
Can you remind us how these two are?
Well, using this Panizurin.
So it's a basically
well,
it's just
T1,
T2.
Sorry.
So when you mutate this T1, T2, it becomes a linear combinations of T1.
It is piecewise linear, depending on the size.
You get linear combinations.
Minus matrix. Well, consider the case m equals 3. This gives you A2. Some geometrical interpretation. So let us come back to the integer case.
No, I'm still confused. So it's like a quiver, right? We have lots of periodicity on the mutation.
This is somehow, in some sense, finite case. Yeah, these numbers are less than 1. And well, this is something, and sometimes roots of units. This is what happens in very few integer cases when you have a finite root system. Well, we would like to have the same. Okay, so let us go back to integer case, and there's a construction by somehow. Well, this is again geometric interpretation of some results of David Squire and Hugh Thomas and Ahmed Salam. Let us take U to be a cyclic quiver. Well, actually, these works also for skew-symmetrizable acyclic matrix. Yeah, but just for simplicity, so let me speak about acyclic. Sorry, for skew-symmetric case only. Yeah, so then Q corresponds to B. This is exchange matrix. By the exchange matrix, I can construct a quadratic form. Yeah, modulus of Bij. Yeah, modulus of Bij. Well, which is the same. Symmetric matrix. So let me denote it by A. Consider A as a Cartan matrix of a root system. Well, of course, not finite anymore. Take simple roots. I should have said that it is the n times n matrix. For roots, let me denote it by E1, En. Oh, let me define for, so I take any vector, a tuple of vectors, vectors E1, Vm, we satisfy the following properties, such that in the basis Vj's are sign coherent. When I take a decomposition of every vector B from Vi from here, or Vj, in this basis, yeah, it's all its coefficients either are negative or non-positive. And the length of Vi, Vj, is variable. So these are somehow two properties. And then I want to define mutation. Of such a collection of vectors. B somehow. Let me write it mu k. And the rule will be the following. So mu k of, which is mu k of Vi, is equal to minus Vi if I is k. The reflection of Vi with respect to Vk in the following two cases, okay, so I should also have a quivers, not only collection of vectors, but I should have some quiver Q prime. If it is bigger than 0, so all entries of coefficients of K are non-negative, yeah, and there's an arrow from K to I in the quiver Q prime, or if Vk is less than 0 and there's an arrow from I to K in the quiver. So if Vk is somehow positive, then we reflect all the heads of arrows from K. If Vk is negative, we reflect all the tails. The vector stays intact otherwise. This is what I will do now, precisely. Yeah, I take the initial quiver Q. Now start with Q and E1 here. So this is actually the mutation of Q with principal coefficients. Okay. Because this E1 in basis EI is 1, 0, and this is 0, 0, 1. Right? Then the statement follows from results of Spire Thomas. And someone says the following, that just mutate to a seed T. Let me denote it by T. Then the following. First, that E and T are precisely C vectors. That the modulus of the so the absolute value of inner product Vi Vj T is equal to modulus of Vij. So first, this rule is precisely the rule how C vectors change. Observation, and the second observation that somehow these C vectors tell us how the initial matrix, how the top part of the change matrix looks like.
Root 2?
Sorry?
Why do you scale so that the lengths are root 2?
No, so mutation as root 2 because I want this to be reflection.
Orthogonal reflection can say.
No, well, this must be reflection. If it is not square root of 2, then this is not reflection.
And it's probably just a very value question. What did you do to make the length of the unit vector root?
Maybe using that other.
I multiply by square root. Well, probably there are some more complicated.
The form that you're using is
Well,
E1,
I start.
E1.
Well, I start with rules of length square root. They don't change, right?
Yeah. The length is the square root of the area itself, or
No, this was the way how I defined the quadratic polynomial. These two. No, well,
yes.
sometimes just to be consistent, what usually happens. And the observation that this also works. So the same minus 2% power m. Oh, no, sorry. This is not, this is matrix B. To have a Cartan matrix, I put here 2, I put here 2, and I put here minus. Express this in terms of Euler form. Somehow, in some sense, it's easier to say about to speak in terms of just usual reflection. Because somehow it gives you some geometry, which you can. Yeah. And using these, yeah, one can somehow, well, it's not too difficult to show that these imply the priorities of the mutation.
By C vectors, what you really mean is this vectors form that you want.
C vectors are, well, I take B, I take identity matrix, I mutate it, but I have here are C vectors.
So you have this below this.
Yes, indeed. So I put here identity matrix. I start mutating, and I get, well, this is my definition of C vectors. Yeah, I think it is. There it is. Geometry. Let me make some remark on geometry. In rank 3. It's a cyclic. Let me write it. In model mutations by reflections. Let me also call this procedure as partial reflection. Split all the roots into just in two parts. We reflect one of them, and we just keep intact there. Okay. We can model mutations by partial reflections. In rank 3, in sphere or Euclidean plane or hyperbolic plane, depending on the signature. It's not precisely what we have here with C vectors, but we somehow can associate with every seed, whatever it is, some collection or some triple of lines. Yeah. Well, again, I will probably not go into details. here. Yeah, and if Q is cyclic, then by the result of Beinecke, Brusle, and Hille, that all PQ are greater or equal than 2. And this implies that what we can do, we can take 3 points on the hyperbolic plane. Say GP is 2 cosh, where P and R. We can model mutations. We take, for example, if we mutate here in this vertex, we take this point and take a line and take a central symmetry of this point with respect to this, and this with respect. This triple of points, that triple of points. And then these numbers will be precisely the entries of the mutated matrix. Somehow one can show this. Why do we need this? We need this to somehow.
Well, can I ask a question?
Yes.
Can you draw the version next to it, like keep the original and then
Mutated version of
just the triangle?
the triangle? It will be. You know, it depends on the rotation of the curve. No, it's cyclic. Yeah, no, since it's cyclic, yeah, it always looks like. Okay, why do this? I want to define finite and finite mutation, right? Well, it is not too difficult to define finite mutation type, but somehow finite type is a bit more tricky because you somehow need to, you know, finite number of what do you have, right? So this is finite mutation type. In this geometry, well, it's quite easy to get, well, not straightforward, but so one can get a classification of mutation finite quivers in rank 3. So mutation finite in rank 3. So what we get, this is right, so myself and Anna, we get just Markov quiver, get a quiver, a series of quivers, 2 cosine of pi over n. Yeah, well, which we call a fine. We have so-called symmetrization of this, yeah, and also H3 and 2 others. H3. Yeah, so here we have 2 pi over 5 And here we have pi over 5 and pi over 4. Let me write h prime, and this is h.
In this big arrow is 2 or is
Yeah, it's a double arrow.
okay.
Well, this is a quiver.
Yeah.
Okay. Yeah, so this is in rank 3, and well, this can be extended. So what we get some free series. I will again not go into details. We get series in rank 4, infinite series in rank 4, and everything else zero root systems. These three series, we don't have anything essential. Finite type. So what somehow you can understand as, yeah, well, finite type means that we can somehow associate with mutations finite number of something. Okay, so to you can get like here. So what we did? We took two roots in the root system, started just reflecting them. We still stay in the root system, so somehow we have only finite number of possibilities. Yeah. Yeah. In this sense, this is a finite thing. Yeah. And one can somehow, well, it's quite easy to see that these are precisely, in some sense, these are finite types, and in rank 4, we also have H4 and some variations. Of H4 prime, where H4 prime means that, like here, yeah, you take. Because, well, we have different combinations. You start with different combinations of roots of H4, but mutating them in the root. Most interesting, of course.
First. Our old friend.
It means that you want somehow to have something like seed. You have some, with every vertex of the quiver, you associate something. Okay. Well, for example, in this particular case,
Not cluster wave, not some.
we don't have cluster variables. For example, like in this situation, we associate roots. We associate a pair of roots of the corresponding roots. When we mutate, we reflect this root. We receive we associate a pair of roots. We have so while mutating, we get finite domain. These are C vectors, but unfortunately, well, unfortunately, when you have angle like that, yeah, these what you associate are not. You may go so outside of the root system, but not too far. Okay.
And do I get finitely many?
You get finitely many. You get finitely many vectors, yes. But somehow, if already for just if you write here 2 pi where, yeah. So this statement does. They're not talking. Well, in some sense, they're not talking. at some point. Well, there's an easy geometry behind it. So what is? Let me just qualify. So normally you start with this cone. So you take the simple roots of your root system Pavel. Okay, these are simple roots. Now let us start with these roots. I2 of 5. Okay, then it's not too difficult to see that I need some different color. That this vector alpha 1 and alpha 2, then this vector is alpha 2 minus alpha with some coefficient. It's not it is not sign covariant in these places.
It's just a definition of finite type. I mean, is a definition of finite type? Find C vectors in this naive way, which they might not be sign coherent. I just ask if there are finitely many.
Yes, definitely. This. Okay, but alternatively, actually, we can a bit modify these. We can just modify this procedure to stay in the root system, to assign vectors a bit differently, to mutate a bit differently here, such that these does not correspond to mutation of the matrix, yeah. But this is somehow the rule is consistent, and we stay with finitely many. We can do it. And so most interesting, still, let me consider usual H4, H3, and I2. If I'm not sure I will go to the end, but
The example of lamp finite mutation type. The example. Okay.
yeah. Next, I want to do unfoldings. But somehow I need to cut. So, well, unfolding was the way to assign to some skew-symmetrizable matrix, matrix. Such that mutations of these agree with the composite mutation. Let me, instead of writing definition, let me show an example. Again, most elementary example. Let me take the matrix B, just G2. Yeah, it is 0, -3, 1, 0. And I take matrix S to be, so here the skew-symmetrizer is 3, 1. So I take two blocks somehow of size 3 and of size 1, and write 1, 1, 1, and -1, -1, -1. So this is D4. Okay. And here I have mutations 1 and 2. And here I have a composite mutation. So here it is mu1 and mu2. And here I have composite mutation mu1 and mu2. So mu2 is a mutation in this fourth column, and mu1 is a product of mutations columns. And what we see that the sum in this block is equal to this, and the sum of entries in this block is equal to this. Okay. So we have somehow, in the column. Yes. Some, thank you. Yeah, so some in the columns. So these are somehow, here we have blocks E1, E2. Yeah. So E1, E2. So, and we have the following properties that EI times EI deal with zeros. Second is that if we take the block EI times EJ and take a column EIJ, and the third is that all entries EI times IJ of the same sign. So you can't have in one block, you can't have positive and negative. These propagate take a corresponding composite mutation of matrix S. All these want to define weighted unfolding. Matrix B is reversible, and I also have my matrix W, so this is matrix of weights, diagonal, with weight BI, diagonal BI, positive numbers, WI, and we say that S is skew-symmetric. S is a weighted unfolding of B with weight B and W inverse satisfies so here this was supposed to be a running example, but there's not somehow too far to run. So let me take S to be 0, 0, 0. Okay, let me take first B to be matrix 0, phi, minus phi, 0, where phi is 2 cosine of phi over phi. Okay, so this is I2 of phi. Where's somewhere here? Okay, and I want to unfold it, and let me take the following matrix. And here I take 1, 1, 1, 0, 1, minus 1, minus 1, minus 1, 0, and weights 1, phi, phi, 1. This is my matrix. Graphically, this corresponds to the following. Well, this is A4. As you can see, this is, so this is 1, 2, weight 1 here, weight 1 here, weight phi here, and weight phi here. And if you somehow multiply these matrix S by you multiply rows by these weights and divide the columns by the weight, what you will get precisely. Well, it's not very difficult. Yeah, well, it's based on the identity that phi squared is equal to phi plus. Okay. So this is the unfolding and some.
What's the reason it's called unfolding?
Sorry?
Why is it called unfolding?
Oh, because of unfold. I had these.
It's folding.
Yes, I had these. Right. And then I unfolded to a skew-symmetric matrix. Well, the point of unfolding is that I have some matrix which I'm not so sure what to do with, and I unfolded to a skew-symmetric matrix for which everything is known, and then I tried somehow to inherit some good, nice properties from above, you know, to my initial matrix. Okay, in the last several minutes, let me come through. Yeah. So further examples. Yeah, and the initial example of this is E8. Weights phi, 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 and phi here, and this goes to H. And if we cut it, we get this. It's from origin of this. So this goes to somehow the construction of Lustig, to constructed homomorphisms of these groups. And so between these Kafka groups, and it's about 83, and Moody and Patera, 93, who produced extended these to projections of the root systems. So the projection works in the following way. If I take alpha 1, alpha 2, alpha 3, alpha 4, 6, 7, and alpha 8, these are simple roots. Yeah. And I have a map. Here, 5 over 5, F. And here I write f of alpha 1, f of alpha 2, alpha 3, f of alpha 4. Yeah, and the image f of alpha I plus 4 is equal to phi f of alpha. The image of this is phi times image of this. Then if I extend this by linearity, root system the map projection between root system of type E8 and root system of type H4 together with the phi multiples. So well, this is not obvious. Immediately obvious that when I extend this somehow map by linearity, which is defined here, then image of a root will be a root or a phi multiple. But this is the case. And this also extends, of course, here, and the same construction can be done for I2. where here we will have a and minus. Here the weights theta 1, theta 2, and so on. 1, theta n minus 2, where not surprisingly theta I is a Chebyshev polynomial of any kind. Okay, so this will be sine of I plus 1 pi over m divided by sine. Okay, well, that's not surprising in this, but somehow this works. We have a weighted unfolding. And in the last minus 2 minutes, let me say at least a couple of words about something like categorification, which we try to do with Drew Duffield. So let me write differently this quiver. Let me, so what was not the notation? Notation was 1, 2, 5, 2, and 5, 1, which somehow means that here this projects to 1, 2, 5. This means that this projects to root 2, this projects to root 2, but here we have weight 1, and here we have weight 5. Write the model category of A4, which will look like this. Yeah, and then we can somehow compute something like dimension vectors. Yeah, we can compute projections, dimension vectors, according to. So what I do, if I have different column, if I had V1, V2 numbers, V3, V4, yeah, I take V1, V2, V3, V4 to V1 plus 5V2, 5V3 plus V. Okay, so I take this sum of these is 2, sorry, because it's 2 and this is. I take a sum of the corresponding values with weights. Then these are alpha models, and these are, let me write it, these df, and these are df of corresponding. If this is a model, this is the projected vector. And there are two observations. The first observation is that this picture preserves weights. So here there's a weight 1, and here. So in all rows of this picture, the weights are the same. Okay. So we have here weight 1, here weight 1, and here weight 5, and here weight 5. It's the first observation. Well, probably I should say theorem. Yeah. By Drew Duffield and myself. Well, but was credit here should go to Drew Duffield, in particular for his infinite patience while explaining the stuff to me. And this is the first one. Yeah. So weights. Well, I should have written all formulas, but well, I have no time for this. Yeah, and so weights along rows. Weight among rows are the same. yeah, we see that this vector is a prime multiple of this yes, and this also propagates. So somehow we know that if two points here, for example, phi1 and 1, goes to somehow they are projected to the same root, yeah, then these we know, but the statement that actually this also propagates through the whole picture under the action of Alexander. Okay. Okay. No, I can't formulate it in short way. Write something here. Yeah, and just the last line. Sorry for going over time. Is that we can also define the functors. So also define the functor root. So this module to this module, and if it already has phi squared is 5 plus 1, so it will be this plus this. Okay. So this is the way. Okay, so and this can be extended to morphisms. So the mod AQ, yeah, has a structure of z greater than 0 of phi category. So we have a category with the action of the semmering. Yeah, and this can be extended category and classifier. This action can be extended somehow.
In that case, when you are applying to this 0 phi, you are getting an object which is not indecomposable anymore.
Yes.
Yeah.
Yeah. So if I multiply phi by say phi 2, yeah, I will get phi 2 plus 2. Phi of 2 is phi 2. Yes, and well, this and we somehow can also define somehow using our unfolding. We can define somehow invariant mutation. But okay, this is probably too much. Okay. Okay, thank you, and thank you too much.
Are there any questions?
I actually have a question with respect to this theorem. Isn't the proof based in some relation within the mesh relations that you have in your federated Euler?
I think yes.
Okay.
But probably Drew can answer these in a bit more detail.
Okay.
Hi. So yes, if you have an Alexander-Rayton sequence, okay, and you apply this functor which is induced from the semi-ring action onto your Alexander-Rayton sequence, you get a sum of Alexander-Rayton sequences onto this as well. So if you look at the Alexander-Rayton sequences with an indecomposable middle term, okay, so these are Alexander-Rayton sequences which have a weight of 1 at the start and the end. and a way to phi in the middle. Okay, and you apply the functor phi on this, you'll get another Alexander-Eiden sequence in the category, which is somehow a phi multiple of this Alexander-Eiden sequence. And you can continue to do this to get sums of Alexander-Eiden sequences. Does that answer the question?
Going back to earlier, you defined these.
We have sign coherent C vectors, and the Leibniz-Levinsky duality allows me to define G matrix. Okay? So if C vectors are sign coherent, if C vectors are sign coherent, then I can define the matrix G to be C inverse.
Always do that.
Yes,
Maybe.
but if well, you can, but then you do not know how G. If C vectors are sign coherent, then there are rules for mutations of G vectors, and they're true. Yeah, so they hold well somehow rules which are written in the Leibniz-Levinsky and somehow just all. So they vectors change precisely as they change in integer.
And coherent in the other way.
We have these G vectors, and yeah. For example, when I mentioned about this geometry about this periodicity, yeah, this is somehow the way. Yeah, how to explain this periodicity.
Fine. Why not defining
X variables and no F polynomials. I don't know where they are. Probably there somewhere.
The chat, maybe, no? Any questions from the Zoom audience?
Here's the question: is can you do something clever with Penrose? Can you do something clever with Penrose tilings in this class content?
Again, for this beautiful talk. Thank you, everyone, for joining.